Alright, welcome back. Here we are in 1.4, solving absolute value equations. We're going to change gears from our inequalities for a moment, but you'll see those enter back in here in a second, in our second part of this lesson. So, solving absolute value. First of all, we need to understand what absolute value is. Absolute value is basically your distance away from zero. And if you've ever talked about distance, just in regular conversation, you rarely talk about distance being a negative value. So if you look at the number line up here on the chart, we have the number -4 and +4. And we notice that they're both 4 units away from the 0 as our reference point. So that's another example of how the absolute value is a distance. It's always going to be the same distance away. So you always have two directions you can go from 0. And you can go to the left or to the right. So another example, 5 and -5, I guess in words, have the same absolute value. The absolute value bars are simply just another grouping symbol that we talked about back in order of operations. So like parentheses and things like that, the bars are also a grouping symbol. We won't distribute into them like we do with parentheses, but we can still operate within them first. So as an example, you have the absolute value of 25 equals the absolute value of -25, which both equal 25. So what you're seeing here is that when you take the absolute value, essentially you're always going to come out with a positive value because the distance from 0 comes out positively. So let's show a quick example. So in the black on the bottom here, you have and evaluate this expression. So I have absolute value bars and I also have a +5 at the end. So inside the bars you see 9 times -2 minus 3 and with the +5 on the outside. Again, you're going to want to apply your PEMDAS rules, your order of operation rules. So we're going to go inside our bars and we notice that there's multiplication happening with 9 times -2. So you crunch that, you get -18 and you still have your -3. So we're still inside the bars and you get -21. So now is when you can actually apply your absolute value. So the absolute value of -21 is +21, and now you can go back and apply your +5. So when you add that, you get your 26. So that's kind of a very basic example of when absolute value could be used with all of these being known values. We're going to get to it when you don't have a known value, when you have some variables. All right? All right, so number 2. Check this out at the top of the board. It's in blue. It says solve just a basic equation with the absolute value involved. So x plus 8 equals 3. I need you to do 2 things. Both of these are equations set up. The first one, you will not change anything about the equation. It's not going to change at all except for the fact that you're going to take your bars off and solve it. So you see that we have x plus 8 equals 3. That's all you have for the first scenario. If we solve that, you do your normal rules. You subtract your 8, and you have x equals -5. So that's one of your answers. We'll have to check that in a second, but that's one of our answers at the moment. The other piece is x plus 8. Notice I did not change what's inside the bars. So that's your first kind of recognition point. Don't change what's inside your bars when you write both of your equations out. But what changes is the equals part. You change the 3 to a -3. So always think about how you have to approach it from both sides of the 0. This was 3, this is -3. So when you solve it, you get a slightly different answer. You see that you get -11. So every time we do an absolute value equation, understand to get rid of your bars, write that equation out, and then secondly, get rid of your bars and write out the same equation but flip the sign of your equals portion. So we need to go back and check our work because sometimes it doesn't always work out. In this case, you see I've got both of these checked off. They do work, but when you check them back with the original problem. Okay, that would be back up at the very top. X plus 8 equals 3. So both these worked. So why don't you try this one right here, pause the video for a second, and model it after the one you just saw. Y plus 4 minus 3 equals 0. Okay? I'll let you pause and you can start that. I'm going to move on to number 4 though. So number 4, down here on the bottom right, has 3d minus 9 plus 6 equals 0. So it's kind of like what you just did with number 3 in the sense that I have this plus 6 that's in the way. So before I can go create my second, my two equations, I have to get my absolute value bars isolated. So I minus the 6 from both sides. I get my absolute value of 3d minus 9 equals negative 6. And obviously you see some things ahead of what I'm saying. But we cannot go any further because this absolute value is actually equal to a negative number. And that's impossible for us to solve. So stop sign, the absolute value bars cannot be negative ever in any of these situations. So make sure you notice that. Don't try to keep going with the problem. Otherwise, you're going to get to a situation where when you check, it won't work. So this is kind of a shortcut stopping point for you. When you have absolute value bars isolated, make sure they equal 0 or a positive value. Okay? So we're going to change gears here, and we're going to switch over. We're still going to talk about absolute value, but it's going to be in the sense of with inequalities. Okay? So 1.6 uses absolute value in its teaching, but we're going to use it also with inequalities, what we just talked about with equations in our and or and the compound situations. So I've got a few notes at the top. It says you must create 2 inequalities per problem. You have to have 2 inequalities in every situation. There are 2 situations that we're going to have to look at. One is your and the other one is your or. So I see there's a little bit of a glare, so we'll kind of raise that up. So on the and problem, if you have a less than or a less than or equal to symbol in your problem with the absolute value bars, I want you to think less than. So just add that D on and just make a mental note that that's what you're going to use. It's going to be an and situation. On the bottom part, if you have or, if you have a greater than sign or a greater than or equal to sign, I want you to think about greater. Instead of greater, think greater. So throw that O in there, and that might be just a simple little help for you to recognize which situation you have, because they're not going to tell you now, like the compound inequalities. This will be more on your own, and you're going to have to decipher the symbol, the inequality sign. Okay, so less than or equal to is the and greater or greater than or equal to is the or. So if we move over here to some examples, you have 2x plus 1 is greater than 7. So my first thing I want to identify is what am I working with? Is it and or is it or? And greater is or. Okay? So I'm going to kind of just lay out the problem. We're not going to solve this one per se, but we're going to show you what are the types of equations you have to create. So I want to make 2 cases. My first case is I don't want to change anything at all about the problem except take your bars off, of course. So I will say 2x plus 1 is greater than 7. That's one of my situations, and I'll solve for that. The second case is where things change. You're going to change 2 things. You're going to flip the arrow, so flip your inequality sign. If it's greater than, make it less than. If it's less than, make it greater than. In this case, we're going to switch it to be less than. And the second thing you'll switch is the sign of your answer. So switch its positive to negative or negative to positive. In this case, we are greater than 7, so it will be less than negative 7. And then you'll solve that one. You're going to get 2 answers again as you go through the solving process. Okay? Let's show you a couple more examples of these 2 cases for each absolute value inequality. Okay, up here at the top left for you guys, example number 2. The absolute value of x minus 5 is less than 3. So new problem. First thing you should notice is that the less than should be and, less than. And I'm going to create my two cases. So over here I say x minus 5 is less than 3. Notice I just took the bars off of that. That's all we did there. So you set that up and you solve it straight away. I added 5 to both sides, and now I get x is less than 8. Nothing changed with the problem except I took the bars off. Notice I also put and. It's not an or problem, so I put and. X minus 5 did not change, but I flipped my sign or symbol and I switched the sign of my answer from positive 3 to negative 3. I've got that circled for you. So now I'm ready to roll. I can solve this. So you add 5 to both sides and I get a 2. So I have x is less than 8 and x is greater than 2. Now you can leave your answer like that algebraically, but you can also combine it into your 3-part compound inequality. So I could say my 2 is on the left and my 8 is on the right, my x is in the middle, and this works out. 2 is still less than 8, so our arrows are pointing the right direction like we talked about in class. And my graph has open circles because of the fact that we're not equal to, and it's everything in between. So remember, we talked about and problems needing to be all or nothing. It can't be anything like an or, this or that. So this is everything in between 2 and 8. Okay? So let's go over here to the top right on number 3. You see you have 6 times the absolute value of p minus 3. Let's see if I can get off that glare. Okay. So what is the first step in this problem? And if you're thinking to divide both sides by 6, you're exactly right. We've got to isolate the bars first. You'll hear me say that in class. Isolate the bars. So when we divide by 6, we end up uncovering the absolute value of p minus 3 is greater than 4. Notice I said greater or greater. So you identify your or problem, and I'm working vertically right here. My first situation is p minus 3 is greater than 4. Nothing changed in that problem. So I solved it. I added 3, and p is greater than 7. So I hold on to that answer, and I work to my next case. So my next case will be p minus 3 again. Nothing changes inside the bars, but now my sign flips around to less than, and my 4 changes its sign from positive 4 to negative 4. I still go through the solving process the same way. I add 3, and I get p is less than negative 1. So I have my 2 pieces of my compound inequality. This is an or statement, and as I graph it, I notice that my circles are wide open, and my arrows are going away from each other, and like we mentioned in our example, it can be this or that. This holds true for the or situation for our compound inequality. So that's a few examples. There's obviously other types that we can get at, but these are kind of just a snapshot of some of the examples you might see on a quiz or a test or just in your problem sets. On the bottom left, I've got a few things to remember. Never change the stuff inside the bars. Never change your content inside the bars because that will stay the same. It's the other things you'll change in case 2, flipping the sign and the symbol. So I refer to that. On the first inequality, don't change it at all for your first case. For your second inequality, flip your arrow and switch your sign. So these are kind of the hot points for this lesson. All right? So if you have any questions, come to class, come before school, anything that you're puzzled on, bring to my attention, and we'll see if we can smooth all that out. And remember, always flip, don't flop.